welcome everybody to session 2 of this sequence of 4 workshops on machine learning. Today, we're going to be looking at a very popular approach to machine learning known as topic modeling, which is actually a broad area, topic modeling. There's different ways of trying to get a computer to work out what the topics are in a set of documents. But today we're going to look at by far the most famous algorithm, which is technically called Latent Dirichlet Allocation. But no one calls it that. Everyone just calls it topic modeling. So this phrase topic modeling can be a bit ambiguous. It actually refers to a whole family of different algorithms, but 99% of the time when people refer to topic modeling, they're actually just referring to this one algorithm. So I'm just going to say topic modeling for the rest of the session, but that's just to keep in mind that actually we're just looking at one particular algorithm, which happens to be by far the most popular topic modeling algorithm. So the session is basically going to go in 2 halves. In the first half, I'm going to try and explain to you how this topic modeling works. And then in the second half, there's a Colab notebook which has some code where we can get the algorithm working. So if you look in the chat there, the longer URL, the one that begins with colab.research.google.com, if you could just click on that and it'll fire up in the background and that'll be ready for us to go when the time comes. But to start with, I'm actually going to have a PowerPoint presentation. So I'll just share screen. Okay, so topic modeling. What actually is it? The commonsensical meaning of it is this: if you have a large number of texts and they're not properly catalogued, how do you find the documents that are relevant to you? That was the original motivating problem for this approach, which really started to be researched extensively in the 1990s. So topic modeling comes out of a field known as information retrieval. And this is the problem. You have a large set of documents. You don't know what they're about. How do you navigate that set of documents and find the relevant ones? So there's various approaches to this, but the idea behind topic modeling was, well, okay, we know what topics are about from the words that are in them. For instance, a scientific article about cats will probably have the word cat, whereas a book about how to do DIY will probably have the word nail in it. But you can't guarantee actually that just because the word cat appears in an article or the word nail appears in a book, that in fact the article is a scientific article about cats, or that it's even really about cats, or that the other book is actually about DIY. Individual words on their own only get you so far. So some computer scientists came up with the idea, well, what we want to do instead of just looking for individual words is we want to find something in between the individual words and the text. And they called these topics. Now, a computer's understanding of a topic is a little bit different to a human's understanding of a topic. When we talk about a topic, we normally refer to something in the world, which is the reference of our discussion. So, for example, we're standing next to an artwork in a gallery and we discuss the artwork. The topic of our discussion is the artwork. In fact, obviously, for anyone who knows Greek, this word topic, it comes from the word for place. So it's like we're placing our attention on the artwork in the world. That's what a topic is. Now, a computer has no idea there's an external world. So its understanding of a topic is a little bit different from what we think. What a computer notices is that when we happen to talk about artworks, we tend to use certain words which are distinct for that topic. So, we might talk about the frame and oils and brushwork and these sorts of things. These are the words we might use when we're talking about an oil painting, for example. Whereas if we're talking about a different topic, like economics, then different words will appear. Inflation, growth, whatever. And of course, the example of growth there in economics also reveals another problem here, which is that the same word might be used in different contexts with different meanings. So obviously growth in an economic context means something quite distinct to growth in the context of genetic psychology, you know, the growth of a child and their mind. So the whole problem of topic modeling is to give a computer a whole bunch of text and get it to work out what the topics are in this second sense of the word topic. What are the clusters of co-occurring words which define different areas of discussion? That's what topic modeling is. And as I say, its original application was in information retrieval. You know, you have a large unstructured collection of texts and you want to find some structure. You know, the best way of doing that is to get a librarian to catalog them, but that's obviously very labor intensive. In the meantime, if you could have an automated process, that might help. But obviously in the humanities, other applications have been found of topic modeling. So I'll discuss a few of those in a minute. But to begin with, let's go just a little bit deeper into what exactly the computer thinks is happening when it's doing topic modeling and what exactly we're asking the computer to work out. So here's an analogy. Basically, when we train a topic model using LDA, using Latent Dirichlet Allocation, we're actually training a type of model called a generative model. What we're actually teaching the computer to do is to generate new documents by mixing together different topics. So here's an analogy. You could imagine what we're doing is teaching the computer to cook. It learns what different ingredients make up each document in the corpus. You know, a curry can be made of a mixture of things like cauliflower, potato, onion, spices. It learns to mix the topics together in order to create individual documents, which are a mixture of topics. It's also known as a mixture model for this reason. In a sense, documents are already a mixture. They're a mixture of words. So what the model is trying to learn is instead of just going from a huge chaotic series of, say, 100,000 different words and trying to mix them randomly together to create documents, it learns that certain of those words tend to clump together, and then certain of those topic clumps also tend to clump together, so it can more intelligently predict what sort of topics a document might be mixed of. Now, there's a really obvious limitation to this approach to modeling. Some of you may have heard of the idea of a bag of words model. This idea of a bag of words model is that the computer actually doesn't really care about the order the words are in. And it knows nothing about the grammatical relationships between the words. It doesn't know that cat is a noun and that furry is an adjective. It just knows that cat and furry are words that tend to occur together when a certain topic, let's say cats, what's called the topic cats, tends to be spoken about. So you can sort of see that in this analogy on screen, that the final output, the particular document, is not a sequence of topics or a sequence of words. It's just a mixture. It's a whole bunch of topics just tossed together. So this approach of topic modeling, as I say, it uses a so-called bag of words model. So we discard some information about the texts. We discard what order the words appear in. And we discard any information we might have about their grammar. You know, sometimes some approaches to text analysis, you actually get the computer to know about the grammatical structure of the text. We just discard that. We in fact also discard the most common words, the 100 or 200 most common words, because those words like the, from, at, they don't tend to have anything to do with a particular topic and can sort of cloud the analysis a bit. So you discard those too. And you just keep the rest of the words, and all the computer knows is how many times each of those words appears in each document. This is a so-called bag of words model, and I hope you can see why, because each document is considered to be like a container that just contains a certain number of different words. And what the model learns to do is I said before, it's a generative model. It doesn't learn to write articles or write documents that you might read. It doesn't generate things like that. This model, it just learns to predict a certain mixture of words given a certain set of topics. So how does it do that? This is the diagram from the original paper by David Bly and Andrew Ng, and I can't remember the third person, where this algorithm was described about 20 years ago. This diagram, I'm sure, is completely meaningless to you when you first look at it. But over the next few slides, I'm basically going to unpack what each of these circles is and show you exactly what this means in practice. And hopefully by the end, the algorithm will make sense. But basically, what you can see here, if you look at the arrows, okay, you'll see where the arrows are all pointing. They all point to a thing called W, okay? W stands for word. So the ultimate output of the model is it's going to predict what word should be included in a new document. That's what makes it a generative model. It learns about the topics of a particular corpus, and it learns to mix them together in order to predict which words would appear in a new document. So that's why this W is at the end. And what we're going to do is see how it gets from a big corpus of documents that you show the model to the ability to predict what word would appear in a document, given what sort of topics this corpus is made up of. So you need to think about this on 3 levels, okay? We've got, on the one hand, the whole corpus of documents, that's level 1, which the model is going to examine to learn from. The second level is we have each individual document, and the model's actually going to learn something about each individual document too. And then the third level is each individual word within each document. Okay, so let's start at the first level, the corpus. And you'll see I've highlighted in the diagram 2 circles here. The little one that's called alpha and the little one that's called beta at the top there. So at the level of the corpus, what the algorithm needs to learn is 2 things. It needs to learn alpha, which is the proportion of each topic that's in the corpus. So I gave you the analogy before of cooking. You could imagine that in different cuisines, there's a different mixture of ingredients. For example, in British cooking, you don't often encounter taro or galangal, but you do often encounter pork sausages. By contrast, in Thai cooking, you're much more likely to encounter galangal, and you're not that likely to encounter pork sausages. So the first thing it needs to learn is, in this corpus, if there's 100 topics, well, how much of each topic roughly appears in the corpus as a whole? You know, if this is a corpus of scientific articles about machine learning, then topics you would expect to appear a lot would be things like linear algebra, probability, statistics, calculus, algorithms, etc. You might expect some other topics that are popular among machine learning to appear, like you might expect a lot of linguistics. Lots of machine learning is based in linguistics. You might expect quite a bit about images of animals, because lots and lots of machine learning algorithms are trained on images of animals. You might not expect so much about films. There's not a lot of machine learning research on films. So if there are some articles that are about films, you would expect that to be rather small. So the first thing it learns is the distribution of topics in the whole corpus. Then beta is the other thing it learns at the whole corpus level. And that is, for each individual word that appears at least once in the corpus, which topics is that word associated with? That's what beta is. So for example, I gave the word growth at the beginning of the talk. Growth would be associated with a topic to do with economics. Okay, that's something, you know, and it would also be associated with biology. It might also be associated with education. So if these different topics appeared in the corpus, you would expect that word growth to have an association with all them. And it wouldn't be associated, for example, with power consumption, electricity production, necessarily, or with some other topic. You know, you can see there are topics where the word growth simply wouldn't appear. So that's what beta is. It's the association of each particular word in the vocabulary of the corpus with each topic. Okay, so a bit like with the k-means clustering, one of the things this algorithm makes the user do is actually pick the number of topics. So you actually have to hypothesize yourself what the right number of topics is for your corpus. So let's just assume that k equals 10, okay? And use k for the number of topics like we did for the k-means clustering last time. So if k equals 10, we're asking the computer to find 10 different topics, sort all the words in the corpus into 10 different topics, and then use those 10 different topics to learn something about the structure of each document in the corpus. Okay, so 10. What would alpha be? Okay, alpha would simply be a set of 10 numbers which all add up to 1. And at the beginning of training, okay, it would just be set equally. So each topic would have an equal 10% chance of appearing. So at the beginning, before the model's learnt anything, it would just be 10 0.1s. And I hope you can see why that makes sense. That alpha is just a sequence of 10 numbers. And that at the beginning, each topic would, the computer begins with the assumption that each topic is equally likely to appear. And then as it learns more about, as it starts to sort things into topics and learns more about the corpus, it'll change these numbers. And over time, they'll all be different depending on what the computer thinks about the mixture of the corpus. Does the algorithm know in advance the number of topics and the names of topics? It does know the number of topics because we set it, and no, it doesn't know the names of topics. In fact, the computer does not learn to name the topics. If you give the topics a name, it's a human name that you give it by interpreting the topics that the computer has found. It finds these clusters of co-occurring words, and if you think a particular cluster is about economics, well, that's your interpretation of the model. That's one of the things about topic modeling. The model itself is interpretable. We saw that last week where the k-means model could be interpreted because you could look at each cluster and work out what it corresponds to, but the neural network model was not interpretable because the parameters inside it don't map onto human concepts. This is an interpretable model, which can be dangerous because you can overinterpret it. So as it learns, as it examines the corpus, it populates this matrix which in this original diagram is called beta. Confusingly, in the Python package we're using, it's called eta, but you don't need to know about that unless you look at the source code. It's called beta here in the original paper. And what beta is it's a big k by v matrix. K is the number of topics, so there's one row for each topic, and v is the number of words in the vocabulary. So it would be normal to have something like in the tens or hundreds of thousands for the number of different words that appear in a corpus, tens to hundreds of thousands. So here's an example, a completely made up example. The computer might learn something like this, that the word tiger is quite likely to appear in topic 1. And in topic 2, the words apple and pear are quite likely to appear, but the words tiger and nail are unlikely to appear. In topic 3, the words apple and pear are semi-likely to appear, and nail is a bit likely to appear, and so on. Using this matrix beta, the computer is able to predict what words might appear in a document based on what topics the document is made up of. And using this set of probabilities alpha, it's able to predict what topics a document might be made of. So at the corpus level, what we have is alpha, which allows the computer to predict the mixture of topics that a document might be made of, and then beta, which allows it to predict what words might appear given that certain topics appear. So this is what enables it to generate new documents. And should rows or columns ultimately sum to 1? Yeah, the rows of the beta matrix, every row should sum to 1. So why is that? It's because this models the conditional probability of a word appearing given that the word has been assigned to a topic. So when the model looks at a document that already exists, okay, it tries to guess what topic each word it belongs to. So it comes along to a word and it says, I think this is topic 7. Now, that word that it's found, it has to be a word. There's a 100% chance it's a word. So once it knows that it's topic 7, it must pick one of the words from the row, okay? So it knows this word is topic 2. Well, the word has to be apple, pear, tiger, nail, or some other word. So there's a 100% chance that it's in this row. So every row has to sum to 1. Yeah, and likewise, alpha has to sum to 1 because every document in the corpus must be made up of a mixture of these topics. There's no leftover. So alpha also has to sum to 1. Another little point that I've illustrated here but haven't mentioned is that none of the numbers are ever 0. That might seem a little unrealistic because there probably are some words that really you'll never say in connection to a given topic. You know, it's hard to think of an example off the top of my head, but if you're talking about lawns, you'll probably never mention Jupiter because a lawn could never mow on Jupiter. A good lawn could never grow on Jupiter. But actually, even just my example shows that I've just used Jupiter and lawn together. So maybe it is actually realistic to assume that every word has at least a small chance of appearing in connection to any topic. But the main reason is that the model can get stuck in a bad position if you allow the numbers to go to 0. So every number has to be above 0 in order for the model not to get stuck in a bad configuration. How is the probability calculated? I'm not going to try and explain the learning algorithm in detail in this talk, but at the end of this slideshow, I will explain intuitively how it works. But it'll be hard for me to explain until I get to the end, but I will get to that, yeah. I will try and explain, roughly speaking, how the model works out what these different probabilities are by reviewing the corpus. So does it review the corpus and then make predictions about a new document based on the corpus? Yes, that's what you're training it to do. You're training it to do that. This might seem a bit weird because you've never ever used a topic model to do this. No one ever, actually I can think of one exception to this, but no one ever actually uses a topic model to then generate new documents. That's not what you use it for. This is a slightly perverse thing. It's a generative model. Okay, and that's how it works, and that's its internal logic. But what people generally do is they train the model and then just examine what it's found. They look at this set of topics and they look at what the model thinks about individual documents. And I'll show you in the programming notebook that you can actually do inference with the model like we did with the models last week. You can actually apply the model to some texts and it'll tell you what topics are in the texts. This model falls into a class called Bayesian Networks. It all works on probabilities and every parameter in the model is meaningful. And one feature of these Bayesian networks is that they can be used in multiple ways, which a neural network sort of can't. A neural network can basically just be used in one way, but these Bayesian networks, because they're a meaningful set of probabilities that actually say something, you can interpret them in different ways and use the model to do slightly different things than it's supposed to do. Yeah, so there's no mathematical limit to the number of words that could be in a vocabulary or the number of topics you could train. There are just practical limits. For example, your computer's memory. If you ask the computer to look at a corpus that has 10 million different words and you ask it to learn 500,000 different topics, you'll need a very, 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 very powerful computer and a lot of time to train that and use it. That's one practical constraint. The other practical constraint is that that many topics and that many words is probably not going to tell you very much. Generally speaking, most of the topic modeling you see, the number of topics chosen is in the tens or the hundreds. And most of the time these models are used on textual data. I'm going to show you an example of it not being used on textual data in a minute. But most of the time it's used on textual data. Most of the time on a corpus that's just got one language, a monolingual corpus. And in a monolingual corpus of any human language, you would never really expect the vocabulary to go much above 100,000. You know, it would be very rare. Of course, if you have a multilingual corpus, okay, so if you've got 5 languages and each language has a vocabulary of 100,000, well, you might end up with more words. And it also depends on the language and what you mean by a word. You know, if you're looking at an agglutinative language like Turkish or Swahili, then actually there might be a lot of words and you might need to do some pre-processing to reduce the number of words. But if you're looking at a more analytical language like English or French or something, then the number of words is very rarely going to be above 100,000. Now, I said that this is the model at the level of the corpus, okay? But I said that the model also operates at two other levels, okay? It also operates at the level of the document and the level of the word, and that's what these squares in this diagram refer to. Okay, so the alpha and beta are just on their own outside any square. That means there's just one alpha and one beta. Okay, so the model looks at the whole corpus, and for the entire corpus, it learns one alpha, which is how much each topic appears overall, and one beta, which is how much each word appears within each topic. Okay, within the square that says M refers to the number of documents, N refers to the number of words in the corpus, M is the number of documents in the corpus. So for each document in the corpus, okay, for each document, the model is going to learn a theta, okay? So if you have 1,000 documents, then the model will create 1,000 things called theta, one for each document. What is theta? You can possibly guess. Theta is the probability of each topic appearing in this document. So there might be 500 topics in your corpus, but realistically speaking, you would expect each document in the corpus, depending on how long it is, to be made up of only some of those. So if you're looking at relatively short texts like newspaper articles, you might expect each newspaper article only to have, say, 2 or 3 topics inside it. If you're looking at somewhat longer texts like scientific articles, you might expect, say, 5, 10 different topics. If you're looking at novels, you might expect dozens of different topics. It depends on the corpus and how many topics you picked and so on. But each document is characterized by a particular mixture of topics. And I called it the probability because that's the mathematics behind Bayesian networks. But of course, there's also, the model does actually sort each document into a set of topics. So it might not look like a probability to you. It might just look like a mixture of topics that the model says each document is made of. But technically, in terms of the mathematical analytic interpretation of the model, it's the probability of each document appearing, each topic appearing in each document. That's because it's a generative model. It's imagining itself creating this document. Okay, so what is theta? For each document, it generates a matrix like this. And it actually generates one theta. Let me rephrase. I said it generates a theta for each document. It does if you think of theta as just a row of numbers, which is the mixture of each topic in this document. Overall, it just generates one big matrix, which has a row for each document and a column for each topic. So you can see document 1 is about 30% made up of words in topic 1 and about 50% made up of words in topic 2. And again, because nothing can ever be 0 in a topic model, okay, nothing can ever be 0. This is why it's a probability and not just a count of how much each topic appears in each document. Topic 3 and topic 4 are at some arbitrary set minimum. You know, I've said 0.001. Probably it would actually be much lower in the actual implementation of the algorithm, but I didn't want to put too many zeros. Document 3, meanwhile, has a bit of topic 1 and a bit of topic 2. Document 2 is almost entirely made up of topic 3. So at the document level, the model learns the structure of each document in the corpus. Based on the words that appear in the corpus, in the document. So on the prior probability of all the documents of the topics appearing overall in any document, and based on the actual words that appear in this document. It combines those two things together to work out the topic mixture of a particular document. And you can see some of the assumptions that the model makes here. It assumes that every document is made up of whatever the topics are that it's learnt. Okay, so it assumes it has a complete set of all the topics. And it assumes that, generally speaking, each document is made up of only a subset. So when it learns the mixture of topics in each document, it tries to keep the number of topics in each document small, because it assumes that that individual documents tend to be more coherent than the corpus as a whole. You know, the corpus is about many things. Each document's only about a few things. That's one of the key assumptions made by the model. When you can wonder whether you think this is actually true of actual human discourse. But, you know, it seems relatively commonsensical. I wonder how this algorithm handles metaphors. That's a great question. It depends on how frequently those metaphors are used. For example, if you have a corpus of poetry, then you would expect certain metaphors to appear very consistently, certain imagery. So the word love, you might expect to be associated with flowers and plants and so on. Similarly, the word anger, you might expect to be associated with thunder and lightning and storms and so on. So if the metaphors are used consistently throughout the corpus, then the model will have no problem. But if you have a corpus of a whole bunch of fairly straightforward documents, and then a small subset of those documents are ironic, so deliberately misuse certain words out of context on purpose for an ironic, then the model will probably take the irony seriously. Now, this might not be a problem. It depends on what you think topics means. You know, one way these topic models are often interpreted in English departments is using the theory of Mikhail Bakhtin, if anyone knows him. He had a theory of language that basically matches what topic modeling does. That language is made up of many little languages, little sets of words and ideas and concepts. And when I speak, I invoke these separate little languages. I use the language of the law. I use the language of the marketplace. I use the language of the family, and I mix them together to produce my utterance. And Bakhtin said, when you use a language, it doesn't necessarily mean you're taking it seriously. There's always some level of irony, always some level, he said. And often it's really explicit, like in certain kinds of literature. But even in everyday speech, there's always some level of irony. You know, when I invoke the language of the law, I always know it's not really my language. I know that it's a language that pre-exists me. So it really depends how far you want to go when you think about metaphor and irony and topic models. You know, maybe the topic model is right when it takes the metaphorical language literally. Because maybe in a sense, all metaphors are literal. It really depends on what you think. But yeah, common sense answer, it doesn't handle metaphors that well unless they're used very consistently throughout the corpus. Right, so that's at the document level. Okay, so it learns this bit matrix theta, which gives the topic mixture for each document. Okay, now we go to the word level. Okay, so we're going to go inside this second plate. So you can see this plate that says M is inside the M plate. That's because, of course, every word is inside a document, isn't it? There's no words that are outside the documents. So that's why that little plate there is nested within. So you can see these arrows too, okay? And you can maybe guess what this Z represents. So W is the word. So here, alpha, we had the topic mixture for the whole corpus, which is used to predict the topic mixture for the particular document, which is then used to predict something else. And you might guess what Z is. If alpha is the topic mixture for the whole corpus, theta is the topic mixture for the particular document, what might Z be, which is inside this little plate representing the word? It's the topic of the particular word, yeah. And obviously a word can't be a mix of topics. It can only be one topic. But you're right in that the model, implicitly, the word could potentially be many different topics. It has to be a topic that could appear in the document, but it could be any of them. So you can think of the word as a set of probable topics, but the model will also assign each word to a topic. Okay, so Z is the topic of this particular word, and that also brings us. You might have wondered. I've said that this M box represents each document, and the N box represents each word. What's this little K box? That represents each topic. So I said that beta was a big matrix that had every single topic and every single word. But for each topic, you can extract just the row that applies to that topic. And in this diagram, that is called phi. I don't know why they've used two different symbols, beta and phi, when it seems superfluous to me, but nonetheless, you can extract from that big matrix that has every topic and every word phi, which is the probability of a particular word appearing in a particular topic. And you can see how the model combines Z, which is the topic for the particular word, with phi, which is the words that might appear in that topic, to predict what W is, or to generate W. Okay, so let me give you a tangible example of how it would do this. So hopefully this will make sense. Let's say you've been scanning along through the corpus and you've come to this particular sentence, this particular fragment of a document. Blah, 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 he continued. I think we should plant an apple here under the wall. So that the model's arrived at this word apple. Okay, first it needs to work out what topic is this word. So it extracts from the big matrix theta the row that corresponds to this particular document that this sentence appears in, which happens to be document 1. And that gives assignments for a whole bunch of topics. And you'll see that the most likely thing is that this word is either in topic 1 or topic 2. So it uses a sampling function, which randomly generates a number based on these input probabilities. And this sampling function will tend to output 2 about half the time, and tend to output 1 about 30% of the time, tend to output 3, 0.1% of the time. It takes the input probabilities and spits out a number based on those probabilities. So in this case, I go sample and call it on theta 1, and it spits out 2, okay, which is the most likely outcome. So that means that Z is now 2. This word here has been assigned to topic 2, right? And then what it does then is it looks up in beta for the row corresponding to topic 2. Okay, so that's row 2 of matrix B, which in this diagram corresponds to phi. So this is what phi or beta 2 is, okay? It's the word assignments for topic 2. So it used theta, the topic mixture for this document, to work out which topic this word belongs to. And then it looks here at the relevant row of the beta matrix for that topic, and it uses that to predict what word should appear in this slot. Okay, so it'll sample this phi, and it'll spit out a word. Could be apple or pear or some other word that's in the topic. In this case, it happens to have spat out apple. Now, this might seem a bit weird. We have the word apple here, and yet we've just asked we've asked the model to generate a word for this slot, but we already know the word. Why are we asking it to generate a word when we already know what the word is? So this is where you get to the training phase. So Jan, hopefully this answers your question from before. If you were just using this model to generate text for whatever reason, then we'd be finished now. It's used the probabilities that it has inside it to generate the text, okay? And just by pure coincidence, in this case, it happens to have generated the same word as some document that actually exists. But in the training phase, what it can now do is another step. So each time it goes through a step of the training, it tries to generate the documents that actually exist in the corpus based on the probabilities that it has inside it. So in this case, it happens actually to have generated the same word as the corpus. Okay, so it's probably going to be happy with itself about this. This is a well-trained model, maybe in the final training step, that's learned some good probabilities already. But what it does at this point is it says, it now goes backwards. It observes that in this case, here is apple. And it says, well, how likely is it that the word apple would appear here if all the probabilities that I've learned were true? So I've just used the word likely, which is a key word in probability theory. Likelihood is different to probability. Probability is forward-looking. It's about predictions. Likelihood is backward-looking. It's about what the true probabilities are based on what we've observed. So I'll give you the classic example, okay? Imagine you have a coin that you're flipping, okay? It can either be heads or tails, and it must be either heads or tails. And if the coin is fair, then it's going to be 50% either way, 50% heads, 50% tails. But if the coin's been rigged somehow, then there's going to be a not even distribution. It could be maybe 60% heads, 40% tails if it's an unfair coin. So the probability describes the fairness of the coin. If it's a fair coin, the probability of heads is 0.5. Now let's say we flip the coin 10 times, okay, and it comes up heads 3 times and tails 7 times. This is where we now ask a slightly different question. There's no question now of probability. We know how many times it's come up heads and come up tails. What we want to know is how likely it is that the true probability was 50%. We haven't observed 5 heads and 5 tails. We've observed 3 heads and 7 tails. And we want to know how likely is it that the coin is fair. There are different approaches to this, but basically you choose the correct likelihood function and you apply it to the observations, and it can tell you how likely it is that the coin is fair given those observations. So that's what the algorithm does here during the training step. Okay, it's made a guess about how probable it is that different topics will appear in the corpus and the different words are associated with different topics, and what the mixture of topics is in this particular document, and what the particular probability of this particular word being a particular topic, and so on. It's got these ideas about how probable all those things are. Okay, it looks at a bunch of actual documents and it says, okay, I've observed these words appearing in these documents. How likely is it that those words would appear in those documents if all my assumptions about those probabilities were true? Now, at the beginning of training, everything's just randomized inside the model. Okay, so it's going to make terrible predictions. And basically, it has a way of knowing which probabilities to adjust and by how much, based on the likelihood of those probabilities based on its observations. And I have to admit, when we look at neural networks in the next 2 weeks, I know how to derive those algorithms. I'm not so good with these Bayesian models, and personally, I don't know how to derive that particular training algorithm, but you could take a look at the literature if you're interested. But that's basically what it's doing. It's estimating the likelihood of all the probabilities it's learned based on the words it's actually observed in the corpus, and then using that to adjust its internal probabilities. The final thing that's generated, so I've used lowercase z here to refer to the topic of a particular word. But one thing the model does generate is a topic assignment for every single word in the entire corpus. And when I say word, that can be a bit ambiguous. Obviously, we can think of the words as words in the vocabulary. So there's like 100,000 different words that appear. Or we can think of words as all the words in all the documents. So you might have 1 million or 10 million or 20 million words in all the documents. This is the so-called type token distinction, if you're familiar with that. So when I say Z here, you see it's an N by K matrix. It's not a V for the vocabulary, but an N as in the number of individual words that appear in all the different texts. And you can imagine every single word from every single document having a row, and then being assigned to a particular topic. So you can see should has been put in, this particular should in this particular document has been assigned to topic 4. This particular plant in this particular document has been assigned to topic 2. Now, in most implementations of topic modeling, this matrix is discarded and you can't get it. In some implementations, you can actually get at this information. You know, you can get at this information. It can be a little hard. but I'll show you some examples in a moment of some applications of topic modeling. And you can get at it, and you can actually look at a document and see which topic each word's been assigned to. And some people have tried to use that as a close reading tool. Like, look, the models assign these particular topics to this particular segment of text, and I make these conclusions about the text as a result. I'm not very convinced by that sort of analysis for various reasons, but you can get at this capital Z matrix and see the particular topic assignments for every word in the corpus if you need to. It can be a little hard, but you can if you really need to get at it. Okay, one final thing that I did mention at the start, but I realize I haven't recurred to, is the fact that one problem is that a particular word, such as apple or ship or whatever, could appear in different contexts with different meanings. And we want this model to be able to know that that word could appear in multiple topics. I hope you can now see how that's possible. Okay, in the big beta matrix that learns the word associations for each word, it's got plenty of room to learn that different words belong in different topics. And the way it learns that is because each document has a different mixture of topics. So it's quite easy for the computer to work out that in this set of documents over here, the word cat is often used to refer to a particular type of heavy machinery that's got caterpillar treads, or it refers to catamarans or something. And over here, the word cat refers to the furry feline creature in these documents. And so it learns by kind of looking at the intersection of each document and the mixture of topics in there, and then each word and the different topics it might be assigned to. It learns to disambiguate different senses of individual words. And it does it really quite well, quite effectively. Okay, so that's the algorithm. I'm going to, for the last, say, 10 minutes of this half, I'm going to show you some applications of topic modeling, and then in the second half, we'll look at some practical implementations of it in Python. Before I get onto the applications, did anyone have any final questions about the algorithm, how it works? Are the words lemmas? The short answer is it's up to you. For those who don't know what lemmas are, it's a particular kind of pre-processing that's done on linguistic data to make the computer understand it better. So this is the problem a computer might have. We know that the word am and the word are in some sense the same word. They're both different forms of the verb to be. And likewise, we know that the word run and runs are the same word, and run and ran. In English, it tends only to be verbs and pronouns that change. Obviously, in some other languages, words can change a lot. There are some languages where the stem of the word can change a lot. I think from the top of my head, I think Hebrew or Arabic. I think a lot of Semitic languages, the actual vowel inside words changes to indicate their role in the sentence. Things like that. And of course, there are many languages, one I know a bit about is Swahili, where words can have lots of prefixes and suffixes all attached to them to change their role in the sentence. Lemmatization is a process where the computer goes through and it converts every single word to its base form. So it would find every single am and it would turn it to be. Every single are, turn it to be. Every single me, turn it to I. Every single us, turn it to we. And this way, the computer after that, when it looks at the text, it doesn't see what we see then. It would say, it wouldn't never see the word us, it would only see the word we. And so it knows that all of those we's are now the same. So it's a way of the computer knowing that different forms of the word are actually the same word. Now, it's not necessary to lemmatize your text for topic modeling to work, but you can. And that's something that you have to work out to do through trial and error. And for those who think wow, that sounds very complicated, don't worry. For many of the world's languages, there's free software already available that will lemmatize it for you. You don't need to learn how to do that yourself. Computational linguists have already done the hard work. You can choose to lemmatize if you want, but you don't have to. And in the example online, I don't lemmatize. It's kind of a bit unnecessary topic modeling, because the whole point of topic modeling is to cluster the words together. So it'll be perfectly capable of clustering different forms of the same word together because they tend to occur in the same context. So this is one model where it's not as important as with some other models. I'll just end the slideshow and go to Google Chrome here. So here's the programming notebook for later on. But just before we do that, I just want to finish this first half by showing you a couple of examples. So here's one relatively famous example in literature, which was done by this fellow here, Matt Jockers, in his book Macro Analysis. He got together a corpus of 19th century novels. There's quite a bit of 18th and 19th century work in text analysis because the books are out of copyright and it's easy to get your hand on lots of texts. So he looked at this corpus of about 3,000 19th century novels and he trained a topic model on them. He selected 500 as the number of topics. And you can read his book Macro Analysis, and he does some different things with it. But if you just look down here, he made the output of the model available interactively online. So we can look at all these different topics, such as classical beauty. Right, I don't think that worked because his website doesn't agree with my internet. Okay, we'll just do the basic theme that appears already. So this theme, he's given it the name animals and beasts. Why has he given it that name? Well, this word cloud shows the top 100 words associated with this topic. And you can see that the top 2 are animal and beast. So if we think back to how the model works, what this means is if the computer assigns a word to this topic, whatever number, let's say this is topic 301, if the computer makes Z 301 and then tries to generate a word based on that topic assignment, the most likely word to be generated is animal. Other likely words are jaws, panther, growl, remains, eye, snakes, showman, arena, etc. Okay, and so he's given this topic the name animals and beasts. And I think you'll agree, this topic at first glance, it looks pretty coherent. You know, and there's some words here that are interesting that might reveal this is a very 19th century corpus. Like, for example, we see the words here, Congo, showman, arena. Okay, so apparently in this corpus of novels, when animals and beasts are talking about, they're animals that have probably been nicked from Africa and used in a circus. That might be one conclusion that you draw. There may be other conclusions. Now, then what does he do with these topics? So he's trained this topic model. So he's identified 500 different topics in these 19th century novels, and he thinks the topics are meaningful. A few things he does is he tries to analyze the gender distribution of the topics. So for every document in the corpus, for every novel, he knows that he knows something about the gender of the author. And he claims he can actually predict the author's gender based on the topics they write about. This topic, animal and beasts, it's about twice as likely to appear in novels written by men than by women. So in his corpus of 3,000 novels, based on his knowledge of which novels were written by men and which were written by women. So that's one thing he does. Another thing he considers is this topic over time. So you can see that among female authors, the topic steadily became apparently more popular over the course of the 19th century. Whereas it seems to have been rather volatile, but more constant among the male authors. Again, which nationality of authors are most likely to use this topic and over time. And he does some other analyses in the book. In a more recent project, he actually got his hands on several thousand best-selling novels of the last 50 years. And he tried to train these different sorts of models to predict which novels would be bestsellers. And as part of that, he used a topic model. So there he used a topic model for a different purpose to make predictions. What mixture of topics is more likely to lead a novel to be a bestseller was the question there. The book's called The Bestseller Code. He does some other things too, but you know, the topic modeling part, you can see how it might be helpful for that sort of question. Okay, so there's one application. Here's another interesting application. So here I'm on JSTOR, and they've got this tool called Text Analyzer. What this does, let me just, is it takes a document, oops, applies a topic model to it, and then tries to find similar documents. So let's see how it goes with this article here. Oh, it's got an error. Yeah, well, we might not be able to get this to work. I might not be able to get it to work. Oh, why won't that? Anyway, I won't struggle with that now when we're trying to run a class. So you can see the idea there. Okay, it's supposed to read a document. It applies a topic model to it to work out to infer the topic mixture of that document, and then it tries to find two documents that have a similar topic mixture in JSTOR. That's what it does. So you might look it up. It's called Text Analyzer on JSTOR. So if you're interested in that, you might like to have an experiment with that and see if you can get it to work. A few years ago, in a now defunct journal, the Journal of Digital Humanities, there was a special issue on topic modeling, which actually, I mean, this guy, David Bly, was the inventor of the algorithm. So he contributed a paper to it. So it's quite a good paper. It's aimed at humanists. You know, he's a computer scientist. Some of his papers are a little hard to read if you're not used to computer science papers, but this one's good if you're a humanist. Oh, there we go. There are some different interesting applications of topic modeling here. Here is a topic model on articles from PMLA, which tries to tell the history of, I guess, literature and language studies in the United States based on which topics have appeared in PMLA articles. I mentioned before that topic modeling isn't necessarily applied to textual data. Okay, it makes sense. It's intuitive how it applies to textual data, but you can actually apply it to anything if you are clever about what you define as a word and what you define as a topic. So in this interesting article, this very rigorous digital humanities scholar, Benjamin Schmidt, whose work I would recommend, is actually very critical of topic modeling as an algorithm. And he says most of the time you get just as good results with k-means clustering, which is much simpler and in many ways more robust. But he applies it in a very interesting way. He applies it to ships' logs. Now, what's a word and what's a document? So for him, a document is a log from a particular ship, and a word is a particular set of coordinates in the ship's log. So what's a topic? A topic is co-occurring sets of coordinates. So in other words, a topic you would expect would correspond roughly to a particular voyage, a particular shipping route. You know, for example, to give you an Aussie example, in the 19th century, when shipping to Australia, you know, was mostly left from Britain and rounded Africa and came along the southern Indian Ocean, okay, you would expect the coordinate point for Sydney to often appear in logs where the coordinate point for Cape Town appears. And you'd also expect Rio de Janeiro, because that was a common stopping point too. So those points would tend to co-occur. You'd hope the model would learn a topic that includes those points, and that topic would correspond to the shipping route between Portsmouth and Sydney or something. So that's how he applies topic modeling. And you can see here on this set of maps, he's got the thing to learn 25 topics, okay? And each of these maps shows points that were assigned to each of those topics. So this is the beta matrix that shows which points, which words, in other words, which coordinate points were most likely to be assigned to different topics. And you can see that it actually seems to have learnt different voyages quite well. Like you can see quite clearly here, topic 14, what shipping route that corresponds to. Or topic 11, what shipping route that corresponds to. Or topic 16, So it's an interesting application. And basically, he then compares it to K-means clustering, and he says, look, K-means clustering works just as well. Let's crack on with the more practical part of the workshop. Now, as I said last week, these programming notebooks, I hope that no one was coming along with the aim of becoming like a whiz-bang hacker in Python, because generally speaking, the implementation of these algorithms is not very complicated from a programming perspective, because the hard work's been done by other people. What can be complicated, though, is something that it's a bit beyond the scope of this course to teach. The hardest part of machine learning is not normally implementing the algorithm. It's knowing which algorithm to implement, knowing what settings to pick, getting the right data, processing it in the right way. When you get the output from the algorithm, getting it into a format that you can analyze effectively. All these sorts of things are hard and they're fiddly, and unfortunately, it's not really possible in a few short workshops to really get a handle on those. They're things you have to do by trial and error on your own, unfortunately. But what I can show you is the basics of actually implementing the algorithm and how to manipulate it a bit, and hopefully that will give you the confidence to go away and do that, the rolling up of the sleeves and getting your research data and everything in a format where it'll all work. Right, so I'll share screen again. Here we are. Now, last week, we were looking at some pretty simple algorithms on a pretty small amount of data, where you wouldn't necessarily get much benefit from using this Google Colab. But topic modeling can be pretty demanding on your computer. So if you've got even a medium-sized corpus, you might like to make use of Google Colab as your default place to tinker, because you'll get a bit more compute resources. Okay, so first thing we're going to do is we're going to connect to the runtime. So up here, I just have this diagram for the algorithm with a reminder of what each letter and symbol represents. And if you click on that link there, slides, it'll take you to the slides I just went through. That's a PDF. They're sitting there on the GitHub page too. So, and just down here, as I said, if you click on this link, it'll take you to a tutorial for replicating basically the code we've got here, but in R, if that's your language of choice. But as I say, Python and R, we're not doing any fancy programming here. It's just invoking some programs people have already written. So it's very similar to do it in different languages. Okay, the first thing we need is some data. So if you just execute these first two cells, and you have to click this run anyway, because I authored the notebook, not Google. This package here, NLTK, if you're going to be doing a lot of text analysis in Python, you'll get used to this package. It's called the Natural Language Toolkit. It contains lots and lots of extremely useful functions and to analyze linguistic data. All sorts of very useful things. It's one of the fundamental packages for data science in Python. One thing that's useful, it's useful for teaching because it has these 20 or so data sets included in it. So one of them, which we've used here, is 19 books from Project Gutenberg, which we're going to use as our data for this exercise. So if you use this nltk.download function, if you know the name of the data set, then you just put the name in there like that and it'll download it. In order to use this data set properly, you also need to download this other bit of data about punctuation. So that's why there's that second thing there. And then once you've downloaded the data, you can access it as a variable by doing this. We've downloaded the Gutenberg corpus, so now this nltk.corpus.gutenberg command is unlocked. And I've just, for convenience, I've saved that as a new variable called Gutenberg. So there's various ways you can access this corpus. If you use this file IDs method on the Gutenberg corpus, it'll tell you the name of each file in the corpus. And I've just saved the file IDs again for convenience as a variable called books. And if you print out that variable called books, you'll see these are the 19 books we've got. Probably a lot of these will be familiar to a lot of you. Emma, Persuasion and Sense and Sensibility by Jane Austen. The Poems of William Blake. Weirdly, 3 novels by G.K. Chesterton. Some children's stories by Maria Edgeworth, one of my personal favourite authors, but not exactly a famous one anymore. Bit of this bloke Shakespeare, whoever that is. Anyway, you can see a bit of a mixture. It's not a very great corpus, really. It's just a toy corpus for playing around with. One of the books by far the longest is the King James Version of the Bible. So it's quite miscellaneous. It's mostly 19th century fiction, but with a couple of other things chucked in. But it doesn't matter because all we're doing is having something to apply the algorithm to. The first step, as I said, is pre-processing. So the library we're going to use for topic modeling is the GenSim library. This is a very useful Python package that contains several different approaches to topic modeling, including the one we're using today, which is Latent Dirichlet Allocation. But you can actually do some different ones in GenSim. It contains quite a few. It contains various different methods for finding structure in a corpus of texts that doesn't have much structure. Topic modeling being one of the most popular versions. So in order to give the data to the machine, we need to reformat all these texts. So I'll show you what format the texts come in. They actually come in several different formats. If I go, we can get the texts as words. Okay, so you see, this is just a long list. I hope everyone knows what a Python list is, closed in square brackets, where each word has been separated and is a separate string. So we can get it as a list of words. You can actually also get it as a list of paragraphs. So in this case, each paragraph in Leaves of Grass has been separated into each sentence. So you'll see here, we have the first sentence of Leaves of Grass, which is just the title in squared brackets, Leaves of Grass by Walt Whitman, 1855. And it also is in a paragraph of its own. So it's got extra square brackets around it. Then we come to the next paragraph. Okay, next paragraph. First sentence of that paragraph is, "Come, said my soul, such verses for my body let us write." And it keeps going, keeps going, keeps going. It's a very long paragraph. I don't know how paragraph is defined for this book. Anyone who's familiar with the book would know that paragraph might not be a very good word to apply to it. Anyway, keeps going. Here's the first sentence still with the first paragraph. And then there's the end of the first sentence of the paragraph and the end of the paragraph too. So you can get it as this nested list of each sentence split into words structured within each paragraph split into sentences. But none of these representations work for the topic modeling. I told you before that topic modeling is a bag of words. This kind of thing here, this isn't a bag of words. They're still in order. This is not a bag of words, it's a sequence of words. That's the first point. The GenSim package for topic modeling, it doesn't want a sequence. It just wants to know how many of each word appears in each text, each document. That's the first problem. The second problem is, and anyone who's done any sort of text analysis on the computer will know, that this for the computer, this here is not really a word. It's a sequence of individual characters, W followed by H, followed by I, followed by T, followed by M. So what we also need to do is we need to assign a unique ID number to each word and then convert all these words into those numbers. So that's the it wants a numeric representation of each document as a bag of words, rather than a sequence of strings of characters. Okay, so how do we do that? GenSim has a built-in object class called dictionary, which will do this for us. If you run this cell, and then I'll step through what all these different lines do. Okay, so first thing is we import this dictionary class from the GenSim library. Okay, first thing we do down here, okay, is what I want to extract from Gutenberg the words for each text. Okay, as a list like this. And I want all the words to be in lowercase. That's a really common pre-processing step. Otherwise, the word leaves with capital L and the word leaves with lowercase l. Python will think they're two different words. So let's just put them all in lowercase. You don't necessarily want to do that, but it does make it easier. It about halves the number of words in the vocabulary. It makes the thing run a bit faster. So here's the code for doing that. Look at each book. For each book, get the words. And then for each word, put it in lowercase and stick the whole thing in a list. This is a list comprehension. If you find this syntax interesting or difficult, email me afterwards and I can help you about it. It's a very convenient way of writing in Python. Okay, then what we do is we get this dictionary class, you see, and we feed it this lowercase version of all the words in all the texts. Okay, and that creates a new thing called the dictionary. Now, what's the dictionary? It records every single word in the corpus and assigns it a numeric ID. And it also knows the frequency of those words in the corpus as a whole, which is very useful because you can do some useful pre-processing. So the first thing we're going to do is with the dictionary is we're going to filter out the 250 most common words. I explained why we do that in the earlier explanation. Because these words tend not to be associated with a topic. They're not very topical. Words like from and at are not very topical, or he and she, not very topical. So there's no point keeping them in the analysis if what you're looking for is topical language. Another useful thing to do is filter extremes. What this says is don't keep any words in the corpus if they appear in less than 5 texts, and don't keep them in the corpus if they appear in more than 99% of the texts. Actually, we're only looking at 19 texts, so I'm not sure this is actually a very useful line, but it doesn't really matter. These are just some examples of some of the pre-processing you can do with the dictionary. And there's keep n. If you give it a list of words that you specifically want to keep, okay, it'll keep them even if they don't meet these conditions. So that's a useful thing this dictionary class can do. This compactify just tidies up the dictionary after you've deleted words from it. Okay, so there's some code that lets you filter out extraneous words that you don't want to include in the analysis. Finally, what we want to do is we want to get the dictionary, and it has this method in it called doc to BOW, which if you unpack that a bit, it says document to bag of words. So if you give a document to the dictionary and use this document to bag of words, it will convert the document from a sequence of words into, well, we'll see, a data structure that assigns each word a number and then says how often that word appears. And we want to do that to every single text in our corpus. So again, we'll do a list comprehension. We'll loop over all the words in the lowercase version of the corpus, all the documents in the lowercase version of the corpus. And to each document in the corpus, we'll apply this document to bag of words method. And that will produce this new variable called bag of words. So I'll just show you what that bag of words variable looks like. Here's the first text in the corpus, which is Emma by Jane Austen. And you'll see word 68 appears 3 times in Emma. Word 143 appears 7 times. Word 198 appears 238 times. This might seem a bit bothersome. Like, what the hell is word 198? Well, you can find that out from the dictionary. Find out which actual string of characters corresponds to each number. So don't worry, there's a way of reading this. That code I just wrote didn't work, and I think I know why. Stupid error. Okay, so now you've got your whole corpus as a bag of words. Okay, all the novels have been turned into this format where each word has a number and then the number of times that word appears in the document. It's a bag of words representation. So if we go down a bit, now we want to train the model, okay? We want to create a topic model, expose it to these texts and get it to infer some topics. So if you don't mind, just click play on this straight away because it's going to take, like when I tested this yesterday, it took 4 minutes. So while it's training, I'll tell you what the different things are that's happening here. So to access this topic model in GenSim, in the GenSim models module, there's something called LDA model. And that shouldn't be surprising. It's Latent Dirichlet Allocation model, LDA model. And I've written all this in a rather expanded format so that it's easy for you to modify. Here are some things you can set for the model that you have to choose yourself. Oh, that only took 49 seconds today. Yeah, okay, great. This is convenient. If it's training that quickly at the moment, then we'll be able to do a bit of trial and error and see what happens. Okay, great. So you pick the number of topics, 100. Okay, this chunk size says how many texts to look at once in each training step. Okay, it batches them together and looks at a series at once and then updates itself, then looks at another set. So there's 18 texts in the corpus, so I've set the chunk size at 9. It looks at half the corpus each time. The main reason to pick a chunk size is based on the amount of RAM that you have available. So if you've got a lot of RAM, like here on Google Colab, I've got 12.69 gigabytes of RAM. Okay, and if you upgrade to the Pro version, you can get even more. So basically, you want this chunk size to be as big as your RAM will allow, generally. Actually, it could be 18 quite easily here. I just picked 9 to indicate what it is, that it's how much of the corpus to look at once. Passes is how many times to look at the corpus as a whole. So this is saying it's going to go through the whole corpus 30 times, updating its parameters each half a time. Okay, each chunk is 9. So it's going to look at all 18 30 times, right? But obviously it's looking at them half at a time. So it's actually going to do 60 updates, if that makes sense, because it's looking at the corpus half at a time. The pass is how many times it's going to look over the whole corpus. You'll sometimes see the word epoch for that. The training epoch means that the algorithms looked at the entire training set. You also have to set this iterations parameter. I'm going to be honest, I actually don't know what this iterations parameter does in GenSim because it seems to be superfluous when there's this passes parameter, but it seems to, the guy who wrote it says you have to set this iterations parameter and I don't really get that. But anyway, there it is. And there's eval every. You can ask the model to calculate how good it is every certain number of training steps and tell you. Unfortunately, the way GenSim's written, when you do this in Colab, you don't get any messages down here. But if you do it on your own machine, you should receive messages, and you can ask it to evaluate the model. The default way to evaluate a topic model is by calculating something called the perplexity, which is basically just a measurement of how I don't really know what it measures. It's a very confusing statistic that's often used in machine translation and these sorts of things. I'd have to remember what it is, but it's a measure of how well the model fits the corpus, basically. Okay, so there's some things to set. This little line of code fixes the error that just scuppered me before. There's a bit of a glitch in the dictionary object at the moment in GenSim, where it doesn't let you go from the number to find out the word. This little line of code extracts from the dictionary the mapping of each number to the word it corresponds to. So I've created a new thing called ID to word. And if you give this to the topic model, okay, then the topic model within it stores the information about what word each number corresponds to, which makes it much easier to read the output. Okay, so you can see we set all these hyperparameters. We got this ID to word thing. In GenSim, unlike in the scikit-learn stuff we were looking last week, you don't need to initialize the model and then you call the fit method to train it. The initialization and training happens at the same time. So you'll see I just create the LDA model. I give it our corpus that we've just pre-processed up here. You know, it's called bag of words, our corpus. Okay. I give it the corpus. I tell it the mappings, what word each number corresponds to, and then these other things we've defined up here, you then give to it. Now I mentioned one confusing thing, that in the diagram for the original paper for this, it calls the matrix that describes the topic assignments for each word beta. For whatever reason, in GenSim it's called eta, and it has an automatic way of training those things built in, and you can just leave it as auto. That's what that auto is. But you can see everything else here is using our settings that we set up here. Okay, so we've trained the model. The next thing is to apply it to the corpus. So it's learned all those different probabilities for different words and topics and everything. Now what we can do is we can apply it to a book, see what topics the book is made up of, and evaluate whether we think this model's learned anything interesting. So here's the interactive part for you. So if you just run this cell, you'll get a list of all the books with their index number. Okay, so whichever book you happen to be interested in, okay, here's our trained topic model that we trained up here, okay, topic underscore model. It's got a method called get document topics. Okay, the documents are all inside this bag of words corpus thing. If you replace this none with one of the numbers, it'll feed the corresponding book to the topic model, and it'll spit out the topics in the output just below. So for example, I'll put in number 11. And here are the topic assignments for Edgeworth's children's stories. So you see what's happened. Of the 100 topics, it thinks that these 6 appear in Edgeworth's children's stories. And then down here where it says topic model show topic, I can type in the number of the topic, like for instance, topic 6, and see what the top words are for that topic. Okay, so there are the top words for that topic. So I might just give you all 5 minutes to have a play here with these, looking at the topic assignments for some of the different texts and then examining the topics. Okay, and in 5 minutes, let's reconvene and we'll hear people's opinions about what the topic model has learned and what improvements we might need to make. Rightio. Welcome back, everyone. I know 1 or 2 people were still having troubles. I'm sorry about that. I've tried so many different platforms to teach Python workshops on, and this is by far the most reliable free platform I've found, but even this one is a little unreliable, it seems sometimes. I'm sorry about that. Okay, so what do people think? What did they find? Let's hear some people's observations about this model, what it learned, what they thought. Yeah, okay, look, so your point about removing certain words from the analysis is a very good one. Absolutely. And obviously, I just did it really, this is just, I have preferred here to do something that's very easy to implement rather than I haven't gone to extensive research about this corpus. You're exactly right. You can definitely make big improvements by filtering out these sorts of things, like even just here on my screen. Obviously, I think these first 7 things shouldn't be in here at all. These are not topical words. Clearly, the first actually topical word in this topic is boy. That's clearly the first one that's actually topical, and it seems to be linked to the rest of this stuff here. It seems to be about rural family life or something. Most of these words. And yeah, your impression that the quality of these topics is pretty low is also pretty inevitable. We've only got 19 texts and we've asked it to train 100 topics. Generally speaking, you want more texts than topics to get good results. You know, Matthew Jocker's 500 topic model was trained on about 3,000 novels. Another thing he does in that analysis is he chunks the texts into smaller chunks. So he actually doesn't give the model the entire novel. He gives it, he splits it up into 1,000-word segments and gives it that. So I could have shown you that as well. And that probably would have gotten much better results, because if we'd split these into 1,000-word segments, then there'd be many, many small texts. And you would expect a little segment of a book to be relatively coherent topic-wise. You know, the whole of Moby Dick obviously is coherently about whales and so on, but there's lots of other stuff in there. If you split it up into chapters or little chunks, it'll work better. In the initial version of this notebook, I'd actually split them all up into paragraphs, but it didn't work very well with this corpus, splitting into paragraphs. So I ditched that and just put the whole novel. The issue of, so you've raised 2 things there. One is, what is a topic? And you're exactly right that depending on which words you include in the analysis, your human idea of what a topic is going to alter. You know, so Jocker's in that big 500 study of those novels, he did exactly what you described. He did part of speech tagging and then he only kept the nouns. Another common thing to do is to filter out all proper names. Okay, if you're dealing with a corpus of fiction, that's important, because that can be important because obviously different novels are just going to have different proper names in them on purpose, simply to distinguish them from other novels. And you might not want to have topics appear which just correspond to the proper names of particular books, because you might not want the topics to correspond so clearly to particular documents. In other cases, you might. Maybe you care about how naming practices have changed over time. So you're right to raise those questions. The big one, you've raised the biggest one of all, though, which is how to validate these models. When these were first started to be used by people in literature and history 10 years ago, I think it's fair to say they were massively overinterpreted because people were a bit naive about them. And you raise all the right issues. The training begins with a random seed. So every single time you run it, you'll get different topics, even with the same texts, the same number of topics. And even if you get almost the same topics, they'll be in a different order. Topic 5 will now be topic 12. Topic 20 will now be topic 100. You're exactly right that it's very easy indeed to overinterpret these topics. And if you're talking about a vocabulary of 100,000 words, it's quite possible that if you look at all the words that have been assigned to a particular topic, you'll see that actually from a human perspective, it's multiple topics, you know, because when you look at like the most frequent cluster of words, they seem to be about one thing. But then if you look further down the distribution, you find there's like a small topic embedded within it, which is different. That quite commonly happens. I guess the quick answer to your question, how do you validate the model? There's 3 ways. Okay, one is to do exactly what you just did. Okay, and try and interpret it and then question your interpretation. And that's very hard. And many people have sort of abandoned this technique now because they don't see a way of being sure that an interpretation is correct. Another way is to apply some metrics that computer scientists have developed to measure how good a topic model is. So I've mentioned one called perplexity, which measures how well it fits to a corpus. There's another one, there's different measures people have also developed of coherence, to say how coherent the topics are using just statistics. So you could use those metrics. That allows you to compare two models and have a basis to say one model's better than the other. But again, what does it mean if the model's statistically coherent? How does that relate to what you actually care about, which is the interpretation of the model? The third approach is just not to interpret the model at all, but simply to use it to make predictions. So remember last week we used the k-means clustering algorithm, which has a similar problem, that it finds clusters and it may be tempting as a human to overinterpret those clusters. But in that case, we could actually compare the clusters. We could use the clusters to predict the species of the flower. And so that gave us an objective basis for utilizing the clusters. Similarly here, okay, in his bestseller code book, Jockers uses a topic model and then checks it against the sales of the books. And he says specifically, I want to predict the sales of books based on the topics in them. And since he knows how much the book's sold, a model, when he's choosing the number of topics and so on, he can simply pick the model that does best at predicting the sales. And he can do what we did last week. He can split a training set and a test set. He actually does something different, which I don't approve of, called a hold one out method, which I think is crappy. A training set test set is a better way of doing it. You can train the model on 80% of your corpus and then test it against the other 20% to see if the model can now predict the sales of those books based on your trained topic model. So that gives you a way of validating it, but at a cost that you can no longer really interpret the model, because you're validating the model by just saying which one can predict this particular other output better. And it may or may not predict that output using the same kind of logic that a human would, you know? There may be reasons why particular topics in the topic model correspond to being a bestseller, which aren't the reason we want it to be. We want it to be that there are certain topics that appeal to readers more. That's what we want. But maybe that's not what the model's doing. But nonetheless, it can at least predict which ones sell better. So that's something. When it's seen in that way, as manipulating the corpus to provide superior data for making predictions, topic modeling is thought of as a dimensionality reduction method. So instead of each book being represented by 100,000 numbers, representing how many times each word appears, it's reduced, and each book is now represented by 100 numbers or 150 numbers, representing the mixture of topics, which can then be fed into a further algorithm for making predictions. You know, and because you've done that dimensionality reduction, the next algorithm may be able to work more efficiently or better. So that's another way of using it. Another suggestion for validating the models, which sounds good as well, assessing how characteristic of a topic a particular word is. Yeah, so you could analyze you could invert it and analyze go from the word to the topic rather than from the topic to the word. And I noticed that the different topics in the model that we trained seem to represent different things. Some topics seem to just represent a particular author, whereas other topics seem to represent things shared between authors. That's an especially big problem in this toy example, because as we know, the number of topics is much larger than the number of texts in this example, which is not ideal. So you're inevitably probably going to get some topics that just correspond to particular authors. I remember when I was working with this, I eventually abandoned it, but during my PhD, I spent some time on topic modeling some Romantic era novels. And the novelist Walter Scott ended up having a couple of topics devoted to him because he was the only novelist in the corpus to use Scotch dialect. So all the Scotch dialect words got shoved into these topics, and then his novels inevitably were full of these topics. So things like that do happen. Okay, well, that's brought us to time. I'll just point you, there's some code here at the end, which you can have a look at to evaluate the model. You can, if you run this this code here, it'll calculate the log perplexity on the whole corpus. So if you train a few different models, you could spit this out. Let's see how it changes. From memory, you want it to approach 0. But I might have that wrong because it's a logarithm. I get very confused by logs. I think you want it to be closer to 0 for it to be better, but you may need to look that up.